Today we're going to talk about the relationship between our pH values and the dissociation constant of our acids. So first up, I just want to review what we've talked about in the last couple of videos about using pH in calculations. So one quick thing to note is that recall that pH was a logarithmic equation. So although the numbers we're familiar with on the pH scale typically stay between 0 and 14, that's not a hard limit or requirement. Any number that comes out of that equation is a valid pH value. So for example, 2 molar hydrochloric acid has a pH of negative 0.3. Now you might get that number and think that you did something wrong. Don't worry about it. That's a totally fine number to have. It's not typical, it's not common, but it's still, valid math. It came out of the equation. It can tell us a value for pH. So to do a couple quick examples to review these relationships. We've got our first example here, a solution where we know that the concentration of hydrogen ions in the solution is 6.2 times 10 to the negative third. Now from just knowing that piece of information, we can calculate the pH, the pOH, and the concentration of hydroxide ions. So you can pause here if you want to try that on your own from memory. I'm going to go ahead and talk through the solutions. So the pH, again, is based on this logarithmic equation. All we do is we take this equation, the negative log, base 10, and we plug in our given concentration of hydrogen ions. So we get a pH value of 2.2. From that, we can conclude that we have an acidic solution because this value is less than 7. Getting the pOH from the pH is the easiest of the steps. We take 14, subtract our pH value, and the resulting number gives us our pOH value. And then to calculate the concentration of hydroxide ions, we're taking that logarithmic equation backwards. We're putting it back in exponential form so that we can solve for the concentration piece of it. So we've got our base 10 raised to the negative of our pH to get our concentration value. Here's one more example, this time starting with a given pOH of 13.65. Again, we want the pH, the hydrogen ion concentration, and the hydroxide ion concentration. So pause and try this one. Here are the answer steps. Again, the pH is the easiest step here. We take our 14, subtract our pOH value, we've got our pH value, a decimal. Again, don't let that concern you. That's completely fine. We've got a low value, so we have an acidic solution. And then our two concentrations here is our base 10 raised to the negative pH and the negative pOH value respectively to get our concentrations of hydrogen and hydronium ions. Alright, so one more thing we need to talk about for today's concept are the strong acids and strong bases. So you may have gotten a table or list last year of these strong acids, and hopefully those are still familiar to you. Hopefully these 7 here ring a bell or look a little bit familiar. You probably want to have these pretty much memorized going into the AP test. There's just these 7. If you see one of these, you should automatically know that it's one of the special strong acids. Now, these are special because by definition, they are strong electrolytes, meaning they dissociate completely in water. They exist totally as their ion form. There's not any part of them that remains as a compound. They completely dissociate. So HCl, for example, our strong acid here, when dissolved in water, completely breaks down into hydrogen ions and chloride ions. There's no part that remains bonded as HCl. Now you'll see this third bullet point says for the monoprotic strong acids, mono means one, protic means proton. So the strong acids that have just one proton, one hydrogen bonded in them, that's all but this one, the concentration of hydrogen ions or the concentration of hydronium ions that they will produce in solution is just exactly equal to the concentration of the compound that went into the solution. And this makes sense. Again, if we dissolve HCl in solution, if we put 1 mole of HCl in our solution, it breaks down into 1 mole of hydrogen ions and 1 mole of chlorine ions. The concentration of hydronium or hydrogen ions we get out is exactly equal to the concentration we put in. So the only one on this list that's not monoprotic is this one right here. For this one, if we put 1 mole of this compound into solution, we will get 2 moles of hydrogen ions out. So this one would have twice the concentration of hydrogen ion as initial concentration of compound that went in. So this one's special. All the rest follow this rule. If we know the concentration of the acid that went in, we know the concentration of hydronium ion that we would use in our pH calculation. Strong bases are going to include the soluble hydroxides, so soluble compounds that contain an OH ion. These are the alkali metals, so anything in the first column of the periodic table bonded with OH, hydroxide, and the heavier half of the alkaline earth metals, so the bottom part of the second column, calcium, strontium, and barium. These are the only compounds of hydroxide that are soluble in water. If you remember our solubility rules, hydroxides typically were not soluble, but when paired with the alkali metals, all alkali metal compounds are soluble. So we do have a couple instances of soluble hydroxides, and that will be our strong bases because, again, they will completely dissociate in water and completely break down into their hydroxide ions. Some other types of strong bases. A strong base doesn't have to include a hydroxide. Remember, it just has to increase the concentration of hydroxide ions in the solution. So a strong base is just a strong electrolyte that increases the OH concentration. So if we go to calculate the pOH of a strong base, we need to know the initial molarity of the hydroxide ions. This means we have to write out a balanced equation first and check our stoichiometry. For example, if you look at the 3 equations at the bottom, let's look at this first chemical reaction. We've got oxygen ions dissolving into water, and as they do, they start pulling hydrogen atoms off of the water molecules. Our stoichiometry shows us that dissolving a single 1 mole of oxygen ions will result in 2 moles of hydroxide ions. Every 1 mole that dissolves creates 2 moles of hydroxide. So the concentration we would use for our pOH needs to be twice the concentration of oxygen ions that were dissolved because they are creating 2 OH ions apiece. In order for a hydroxide compound to be a base, it must be soluble. It doesn't matter if you've got lead hydroxide, it doesn't count as a strong base because that is a compound that's not soluble in water. If it's not going to break apart, it's not going to contribute any of its hydroxide ions to the solution. And on a similar note, bases don't necessarily have to contain the hydroxide ion themselves. Again, looking at these 3 reactions at the bottom of this slide, all of these are strong bases. All of these produce hydroxide ions in solution, but none of the 3 reactants actually started with the hydroxide themselves. So they don't have to bring the hydroxide ion in with them. They can just result in its creation. All right, let's look at an example. So as I said, oftentimes strong basic solutions don't come from hydroxides. They exist as the result of other reactions. So sodium oxide and calcium oxide are two really popular metal oxides that are used to produce strong basic solutions. So to see how this will work out, let's take this example and find the pH of a solution that's formed by dissolving 0.01 moles of sodium oxide in enough water to produce a liter of solution. So our only piece of given information, we know the concentration of sodium oxide we're starting with because we know we've got 0.01 moles of it per 1 liter. So we've got a 0.01 molar solution of sodium oxide to begin with. The first thing we need to do is write out a balanced equation so that we can figure out what our initial concentration of hydroxide ions in this solution is going to be. So here are the steps for that. Our reaction then is going to be sodium oxide reacting with water to produce hydroxide ions and sodium ions. And when we balance that equation, we find that every 1 mole of sodium oxide that reacts is going to produce 2 moles of hydroxide ions. So the concentration of hydroxide ions in this solution is 0.02 molar, 0.02 moles per liter. It is twice the concentration of the sodium oxide that went in, because every one of these that dissociates creates 2 hydroxide ions. So we've got twice the initial concentration of this compound. That's the hard step here. Once we have that equation and come to that conclusion, we can simply plug that concentration into our logarithm equation to get a pOH of 1.7. So we plugged in the OH concentration, we got pOH. And then from pOH, again, it's so easy to calculate pH. We just subtract that number from 14. We've got a solution with a pH of 12.3. So that's a pretty high pH. We've created a very basic solution without having to add any hydroxide compounds into it. Here are a couple other examples for you to try. So take these couple of compounds, figure out if they are going to lead to hydroxide or hydrogen ions in solution. And then from that information, you can calculate the pH and the pOH. I'm just going to put the answers up. You can try them in your notes and compare your answers. These are the numbers you should have gotten. Now, if we can have strong acids, that means necessarily there must be weak acids out there. So weak acids are only partially ionized, only partially dissociated in solution. It means that when we add them to water, some of them break apart, some of them dissociate, but some of them stay bonded together. They don't dissociate, they don't contribute any hydrogen ions to the solution, they stay as their compound. So in the end, we end up with a mixture of ions and unionized acid compounds in our solution. In other words, we've got an equilibrium happening. So in the general equation on this slide, we've got any acidic compound here, and a element or compound bonded with a hydrogen would be in equilibrium with hydronium ions and the conjugate base of that acid, so the remaining compound without the hydrogen. And just like last unit, we can write an equilibrium expression for this reaction. And we call our equilibrium constant the acid dissociation constant, Ka. It's just like before, we've got our products over our reactants. The square brackets denote that we care about concentrations. And again, see that water, H2O, is not included in this expression because it is a liquid. We only care about aqueous and gas phases because they are the only ones with concentrations. Now here I've written it in a form looking at the hydronium ion. Again, remember you can also use just the hydrogen ion as the second row does and write the equilibrium expression based off of hydrogen ions. The hydrogen ions and the hydronium ions are completely interchangeable. It just depends on how really accurate you want to be with what's going on in your solution. So let's go back to those dissociation constants. Again, we've got our generalized equation in red and our equilibrium expression for it. We call that the acid dissociation constant Ka. And we're going to see in a second here that we can use this in any way we would have used an equilibrium expression in the last unit. So we're just in equilibrium 2.0 right now. The Ka value tells us a couple of things. First off, the larger it is, the stronger the acid, because remember Ka is products over reactants, dissociated ions over undissociated compounds. So the larger that K is, let me go up a slide, the larger that K is, the larger these values have to be. The more dissociated, the more ionized the substance is. So a large Ka means we've got large dissociation, a very strong acid. If our value is much, much larger than 1, it indicates to us that the acid is completely ionized. It's a strong acid. It 100% all breaks down in water. None of it is left, or very little is left undissociated. And this chart just has a couple of examples of different acids. We've got their name, the structural formula, the hydrogen ion highlighted in blue is the one that breaks off in the compound. You can see in some of these there's more than one hydrogen available, and it's always a specific known one that dissociates. And then we also have listed their conjugate base, what's left over when they lose that hydrogen, as well as their equilibrium reaction and the dissociation constant for them. One other thing we can calculate that goes hand in hand with this is percent ionization. This is just another way to describe an acid's strength. So again, for this same general reaction, the percent of the compound that ionizes would be the concentration of hydronium ion created, because that tells you how much hydrogen broke away and dissociated and ionized, over the initial concentration of acid you included. That's what the 0 down here means, initial. And then times 100 to make it a percent. So if we added some amount of compound, whatever amount dissociates and creates a hydronium or hydrogen ion can be used in the numerator here and divided by that initial amount to tell us what percent of this initial amount broke apart. All right, so this next part is going to seem very, very familiar to you, I hope. Again, we're just going to do our same steps from equilibrium now applied to acid-base reactions. So we do have a method, a way to relate our dissociation constant and our pH. Because again, we recognize that weak acids are just in equilibrium. They've got their dissociated ions existing in equilibrium with their undissociated compounds. And so we can use the normal equilibrium calculations that we know and love to figure out what their equilibrium concentrations are going to be. So there's two ways we can do this. We're going to go through this first one. The pH can be used to calculate the equilibrium concentration of the hydrogen ions that result. So we're going to go through an example, but to summarize the steps to do this, we need a balanced chemical equation for the equilibrium. We need an equilibrium expression for K, and then we will use an ICE table, just like before, to find the concentration of hydrogen ions that's resulting from the pH. Once we have all these concentrations at equilibrium, we can plug those numbers in and solve for our K value. Alright, let's see this in an example. We're given the pH of a solution. We've got a 0.1 molar solution of formic acid. So we know that the initial concentration of formic acid, HCOOH, is 0.1 molar. We're at constant temperature, and we know that the pH at this temperature is 2.38. We want to calculate K, the dissociation constant, for formic acid at this temperature. So the first thing we need is a balanced equation, which is written here. And then we need to write the equilibrium expression for this equation. So just like before, we put our product concentration over our reactant concentration. And now it's time to make almost time to make our table. So to calculate Ka, to calculate an actual number there, we need the equilibrium concentrations of all three of those compounds. Now we can find the concentration of hydronium ions from the pH, and of course, looking at the stoichiometry in this reaction, we know that whatever the concentration of hydronium is must be equal to the concentration of this conjugate base as well, because they have one-to-one stoichiometry in this reaction. Every one of these that's created also results in one of these. So we'll do that first. Knowing that the pH is equal to the negative log of the hydronium concentration, we plug our pH in, and we can solve for this concentration by putting this log back into exponential form. We move the negative over first, and then we go back to exponential form. Our base 10 raised to that negative pH gives us the concentration of hydronium, which again must be equal to this concentration as well. Now let's apply all this information we have. Let's put it into a table so we can see it clearly. So we'll set up an ICE table just like before: initial, change, and equilibrium concentrations of our reactant and our products. So we started, this was a given number, we started with this initial concentration of formic acid. And in the slide above, we calculated the concentration, we calculated the concentration of these two at equilibrium. And so we know how much they are changing by. We calculated these boxes. They went from 0 to this value, so we had a change here equal to that calculated value on the previous slide. So if these went up by this amount, this one, again, due to the stoichiometry of our equation, must have decreased by the same amount. So here we just take our initial concentration, subtract our change, we've got our final concentration. Note here that rounding for significant figures results in basically no change in this concentration. There was such little dissociation that while these went up in concentration, subtracting such a small number from the initial concentration was fairly imperceptible. Just a rounding error at this point. So that's something we'll keep in mind on later examples as well. But just note that. These increased, but they did so by such a small amount, we really didn't notice a huge change here in our initial concentration. But for now, let's just take these final concentrations that we discovered, and these are the numbers now, these equilibrium concentrations, that we can plug back into our K expression to solve for our dissociation constant. All right, And so that's one type of problem. We successfully calculated Ka from our pH using a balanced equation, our logarithmic relationship of pH, and an ice table. We could also calculate the percent ionization of this process. Again, that would just be the hydronium ion that resulted over the initial compound that was used. And so we had our equilibrium hydronium ion concentration, we had our initial compound concentration, and so these numbers get plugged in to give us our percent ionization of 4.2%. All right, here are a couple other of examples for you to try. They work out the same as the previous example. So you can try these if you want and then come back and check your answers. You should be able to follow the steps on the preceding slides exactly. They will work out pretty much the same. Here are your answers if you work those out and want to check. All right, so we could also go the other way for that calculation as well. In the last example, we had pH, we calculated K. We could also use K to calculate pH. So a couple points of background information here. The percent ionization that we calculated on that last slide, or a couple slides ago, is related to the equilibrium concentration of hydrogen ions and to the initial concentration of our acidic compound. The higher the percent ionization is, the stronger the acid, because the higher the percent ionization, the more of the acid that's breaking apart to create hydrogen ions, and the stronger the acid. If we have a weak acid, the percent ionization actually decreases as the molarity of the solution increases. This is counterintuitive at first, and I'm going to show you a graph on the next slide to mention this again. So for example, acetic acid is 2% ionized if it is 0.05 molar. But if we increase that concentration to 1.5 molar, we would find that it's only 1% ionized. Again, I'll show you a graph of this on the next slide. So for this type of problem, we are also going to use an ice table to determine our concentration of hydrogen ions. And then once we know that concentration, we can use the logarithmic equation to calculate pH. Now it's important to remember that we may have to substitute X in our ice table for pH if necessary. We might have to do that and solve for X first, just like last unit. Alright, so here's that graph I was talking about. As you can see, we've got percent ionization on the y-axis and acid concentration on the x-axis. And again, as we increase that acid concentration, our percent that is ionized goes down. It's a bit counterintuitive. So let's try an example of this type of problem. We would like to calculate the pH of a solution that has a concentration of 0.3 molar acetic acid at 25 degrees Celsius. So first off, we see acetic acid. We don't recognize it as one of our special 7 strong acids, and so we know that it's going to exist in an equilibrium with its dissociated counterparts. So first off, we write that balanced equation. Our acetic acid plus our water, creating the hydronium ions and a conjugate base. Now we are also given the dissociation constant for acetic acid at this temperature of 1.8 times 10 to the negative fifth. So this is all of our given information. First up, we will write our equilibrium expression. So we've got the concentration of our products over the concentration of our reactants. And then we need to set up our ICE table. So we were given the initial concentration of acetic acid. We assume that the initial concentration of these pieces was 0 because none went into the solution. They're going to be created as products later. And we are not sure yet how much our concentrations are changing by. So we will let that change be x. We will assume that this concentration goes down by some amount x, and as a result of the stoichiometry of our equation, these each go up by that amount x. Now we've made an assumption here for our equilibrium concentration of our reactant. Just like the last example when we saw that x came out to be a very small number, and so subtracting it had really no effect, we're going to assume that x is again going to be very small compared to 0.3, and therefore will be considered negligible. We're going to ignore it since we know that this is a weak acid. We know that not a whole lot of it is going to be dissociating. Alright, so once we've got our table set up, these equilibrium values can be used and plugged into our equilibrium expression. So we had products over reactants. We put in these values here at equilibrium to get an equation, which we could then solve for x, as we have done. So we get that the concentration of hydronium ions is equal to about 2.3 times 10 to the negative third. Finally, that concentration is what we will plug into our pH equation to calculate the pH of our solution. This 2.64 would be our final answer here. Now, a note on that big assumption we made. We go by what's called the 5% rule. It says if x is greater than 5% of the initial value, so the initial concentration of our reactant, we cannot consider the change in that concentration negligible, and therefore we would have to use a quadratic equation to solve. However, if x is less than 5%, it is okay to consider that change negligible. So let me go back to our chart. X here came out to be less than 5% of 0.3, so this assumption was okay. If x was not going to be less than 5%, we would have had 0.3 minus x here, x and x. Let me go back one more. In this expression, we would have ended up with a quadratic equation. We would have had x squared on top still, but 0.3 minus x on bottom, and we still could have solved that as we did last unit with the quadratic equation. So if you want to prove this to yourself, go ahead and set that up and solve for x under those conditions and compare your answers. Here are a couple other practice problems if you want to continue practicing this problem-solving method. Again, if you follow the steps in the slides before, you should be able to do any of these pieces. And so the answers are also posted, so you can check your work. All right. Thank you again for listening. Let me know if you have any questions over the examples done in this lesson or on the homework problems as you go to apply this.